Let's improve the Dijkstra algorithm by adding the binary heap data structure to its internal implementation. Okay. In the previous video I already implement this type class which hide from us the internal implementation of the binary heap, and actually we didn't use a binary heap, we use a list, but this interface behaves like a binary heap for us. Okay, and now I want to speed up this thing by changing its implementation. First thing, I want to change this type class a little bit because I think we can simplify it. First thing, here I want to, so I will remove this mDelete because I will do this extract minimum in such a way that it's extract at first the minimum element and then it is delete also from a binary heap this extracted minimal element, and that's why they need to return here not a pair of the node and its key. They need to return here also the modified queue. Okay, this is first thing. And second thing, this is range that I use for updating another queue. So we can simplify it by changing this queue to a list of some nodes and its case. Okay, so we didn't need to create a new queue to modify the elements of our binary heap or priority queue. Also, I want to remove this instance of mapping here. So we actually they use not list, they use map, and I remove it from here. And I will return this folder, remove this foldable from here, and state like this. Of course, I add ordering key here, and I will change this v to n. It's I mean this in node type. So let's change it everything everywhere. So like this, I think. Okay. Okay. Now I need to import the binary heap which we implemented in one of the previous videos. Okay, I import binary heap module, import by heap, and this is let's do it with qualified by heap as heap. Okay, and actually this is the module of this binary heap we already implemented in previous videos, but now in here I edit it as a model. So I add module here, and here is our implementation known in the previous videos. I only add one method here, the member. which allow us to check any container, abstract container, that it has some node inside of it. So it asks me the question, is the node inside this container or not? And you can see this boolean value and some container as a second argument. And also I changed, in the previous video we implemented as a max heap with extracting the maximum elements. That here for the extra algorithm I need the extracting minimum element, and I change it to a minimum mean binary heap. So this is very easy to do. I just change these signs here and in insert function and here. Now let's return to our Dijkstra algorithm implementation, and having this new type class, I need to a little bit modify the main algorithm. Okay, the first thing here, now we extracting the minimum algorithm, the minimum k, and we need to in one operation we modify our q. So this means that here I not just extract the element, I will also get the q. And here I doesn't need to delete this element anymore. I need to do the updating, but not on the dist. I need to update the queue. Okay, and also I think I didn't because I changed the updating of the elements. Here I will use this list of pairs, and here I also need to remove this. I don't need to use map anymore. I just update the nodes and the case, and here we have nodes and the case in such order. Okay, and here I have a node and the key. Okay, now let's write some type signatures, new type signatures. Okay, I will change it first with this h to n, this closer to our node name, and so here we have some graph, some nodes starting from which we want to find all the paths, and as a result they return the map to each node, and the corresponding mapping is a distance to this node. Okay, and actually here I need to change this type signature. So I have this, so I will also change to nodes here, and the first element of our iteration function d underscore, the first argument is mapping of the found of the nodes to which we found our paths. So we use this type here, but in the second type we will use our container which we implement in the binary heap. So I need to change it here to this type, container array m. So this is a container which implements some container on which we looks like an array, but it is implemented via two maps. Okay, the first map contains the, so let's look how it's implemented. The first map is a map which maps the integers to our pairs of case and node, and the second map is the mapping from our nodes to the indexes of this first array, so for faster lookup by a node. Okay, and we use it here, and first element, the k here is a distant type, this type with L, and the second argument is our node. Okay, yes, we have some container which contains the mappings from a distance to our nodes and we can actually not a mapping but a relation between the distance and the nodes, and its container is actually in its internal implementation behaves like a binary heap, and we can easily and fast extract the minimum from here. Okay, of course here, because I'm not using maps anymore, I need to use the container member function to check if our vertex is in our dist container. Okay, and of course here we're using our dist as mappings, but here to check the emptiness of our container we can use the length function, and it must return the 0. In this case we can say that our priority queue is empty, and we can stop by defining our function as f. This is the list of the pairs, this is the map, this map which contains the nodes and its distances. Okay, and now we need to instantiate our Dijkstra priority queue type class for our CRM data type to be able to use it in our as priority queue in our main algorithm in this implementation. So we start this with instance dpq and our container, and here we need to implement these two methods. Okay, the first one is extracting minimum, which provides at first argument we need to provide at one argument we need to provide our queue, and we can use the heap extract min function from our queue. So actually we use this function extract min, and it returns to us the maybe of pair of the pair which contain k in the node and container. So this means that we need to adjust this thing from extract the value from maybe. So here we have this maybe type, and if we extract it from mjust, we will receive exactly this type. Next thing, we need to implement the update function. Here we have as the first argument our q, and as a second argument we have the list of the values which we can use to update our q. But we updating only if the element is less, okay, if the k is less. And let's name this argument as list L. And how we will do the insertion. Okay, for insertion we have in our binary heap we have this function ins, which takes some container, some pair k and node, and returns a new container. So actually it returns a binary heap. So we of course we can use this function. Let's look at its type signature, but no, let's not look at it. Actually we can use a fold function, fold left, I think, function. Let's look at it, type signature. So it's take some foldable, this is our list, and it takes some initial value is our q. So let's write this here, fold L. We need to provide some function, folding function here. Let's keep it for a moment. Here as initial we will provide our q, and as a foldable we will provide our list. And here I need to define some function, okay? I will call this function ins, and I need to define it. So this ins function must have this type signature. As a first argument it will receive our q, initial q. As a second argument it will receive some pair from our updates, okay, updating list, like this. And I just on pattern match this pair as node and the k. Okay, and now I can write the body definition of this function. Okay, how to do this? So the first thing, we need to check the k. If this k from the updating list is less, only in such a way we need to do update. If this k is less than node k, I will define it later, then we need to modify our q. And to modify it we have methods, two methods of updating q case, which we implement here. So this is the update to low value. Let's remember its type signature, it's take node, it's take k and q, and produce a new q. And here we can provide the node. Let's look at it again. At first node, then the k. So here they provide our updating node, then they provide our updating key, which we can pattern match from here, and as the last argument they provide our queue. Okay, and otherwise, if the key is greater or equal than our node key, then they need to stay our queue as it is. Okay, and they do this. We don't do any modifications. Okay, and now I need to define nk. Okay, nk, how can I define it? Where nk is equal, actually I need to extract the pair, the node and the key, and after I do this I need to take the first element of this pair. Okay, and we have function for this. Let's look at this function. In our binary heap they have this function which takes q, its index, and returns a pair. So I need to take first element of something, for the extract from our queue the element with some index. Okay, here we need to provide some here we need to provide q, and here to provide our index, but I don't know my index, but I can get it with this method, with this function, sorry. So I need to provide q here and the node. Okay, and let's write this. I provide q and our node. Okay, and these things should return to me node k. Okay, with which we do these comparisons. Okay, I think this implementation should work. Okay, let's add this module here. I think we can try to compile. So load our file. Sorry. Of course, errors. Many errors. So one problem here, I'm not here the dists. Which type have the dist? Dist is this is the second argument, so its type is this type, but I use the old map, and for built-in heap from a list of pairs they have some function, build heap list, which returns which receives this list of pairs and produce the container to us. So, and I need to use it here, build heap from a list. Okay, and what it gets a list of k and nodes, but here we have nodes and k, so I need to swap this thing in reverse order. Okay, Let's try to recompile. No, error still happens. So, and I think problem is here that here npattern match is a node and no distance, but actually if we look at our min, we have a first k and then a node. This means that we need to reverse this thing. So no distance and node. And now let's try to compile. Yes, it recompiles. And now let's try to run our function with some graph. So we have this graph G here. You can see this is its edges. And what if I want to find all the minimum paths from for this graph G from path A? I want to find all the minimal paths to every node. We'll run this and we will receive that from A to A we can run the distance 0. From A to B they can go with the distance 1 minimal. From A to C with distance 2. From A to V with distance 1, from A to X with distance 2, and so on. From A to Z with distance 3. Okay, this means that they have this implementation. I think it is a very fast implementation because it uses a binary heap to find the minimum. Very fast finding the minimum value. And actually the binary heap, our binary heap internally use a data map, so it has some kind of tree there under its implementation, and it allows to do the most operations in the log n time. But if we change this internal implementation of the binary heap here for our container, if we use something other data structures here, not maps for example, but hash maps, we can speed it up to constant time. But I will stay with this implementation. I think log n time is also good enough. So I will put this code in the gist, and you can find link in the description. Thanks for watching. Push like, push subscribe, and write comments if you found any errors. I don't do any testing. And thanks you for watching. Bye bye.